Alright. So this next video for week 5, deals with the next two sections from chapter 3. And so for today we have, in terms of related rates, linear approximations and differentials. So related rates. So for example, a question like this. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius increasing when the diameter is 50 centimeters, right? So what do we know? Well, we know that the volume, we know that dV dt, the change in volume with the change in time, is 100 cubic centimeters per second. We know the diameter is 50 centimeters, which means that the radius will be 25 centimeters. We also know that it's a sphere, and we're looking in terms of the volume and the radius of a sphere, and so we need to know the formula for volume of a sphere. And so volume of a sphere is given by 4/3 pi r cubed. And what we want to find is how fast is the radius changing with respect to time. So we want to find dr dt. Right? So what we're going to do is we're going to use this equation, and we're going to find the derivative with respect to t. Right? So we had v equals 4/3 pi r cubed. We're going to take the derivative with respect to t, and so we'll have dv dt is going to be 4/3 pi. Derivative of r cubed with respect to t will be 3r squared dr dt. So we get this, right? So let's simplify this a bit. So we get dv dt. The 4/3 and the 3 will just become 4 pi r squared dr dt. Right? So we have that. Right? Well, now we can take the numbers we have and start plugging them in. So dv dt they gave us, we know that's 100, is going to equal 4 pi times 25 squared dr dt. The opposite of multiplying is to divide, so we'll divide both sides. So we're going to divide by this. And we'll divide this. And we end up that dr dt is going to come out to be 0.0127. And that'll be centimeters per second. So the radius of the balloon is changing at a rate of 0.0127 centimeters per second in regards to this problem. So let's go through another example of how this works. And so this time we have a ladder. Which is 10 feet long. Rest against the vertical wall. A vertical wall. If the bottom slides away from the wall, at a rate of 1 foot per second. How fast is the top of the ladder? Sliding down the wall. When the bottom. And the bottom of the ladder is 6 feet. So we got the question. So let's go through it one more time. That's what we got here. So we got a ladder 10 feet long, rests against the vertical wall. If the bottom is sliding away from the wall at the rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the ladder is 6 feet from the wall? So let's first draw a picture. So we got the wall, we got the ground, we got our ladder, which is like this. We know the ladder is 10 feet. We know the distance from here to here is 6 feet. And we know the ladder is moving this way at the rate of 1 foot per second. And we want to know what's happening in terms of this. We want to know what this motion is, the ladder sliding down. Well, if you look at this, we have a right triangle. And so we have in terms of the good old Pythagorean theorem. So we got x squared plus y squared equals 10 squared. So x squared plus y squared equals 100. Okay. Again, we're going to take the derivative with respect to t. So d dt. So if I do this, we get 2x dx dt. We get 2y dy dt. And then the derivative of a constant is 0. So we have that. Well, what is y? Well, I know x is 6 feet. So we can get what y is because we have our Pythagorean theorem. So we need y first before we go any further. So we got that 6 squared plus y squared equals 10 squared. So 36 plus y squared equals 100. Subtract the 36. So y squared is going to equal 64, and so y is going to be 8. Okay? So we know what y is. So now we can take our numbers that we have and let's plug them in, and we can solve for what we want, which is dy dt. So we're going to have 2 times 6 times 1 plus 2 times 8 dy dt is going to equal 0. Well, 2 times 6 times 1 is 12. This is going to be 16 dy dt. That's equal to 0. Let's take the 12 over to the other side. And so we get 16 dy dt is going to equal negative 12. The next step is to divide by 16. And we get that dy dt is going to equal a negative 3/4 or a negative 0.75 feet per per second, and negative just means that, again, it's sliding down the wall. Right? So we know the rate at which the ladder is going down the wall. Right? So again, in terms of, we get our equation, whatever it is. So in this case, we use Pythagorean theorem. Take the derivative with respect to t, and then solve for the missing value, which was dy dt. So let's do one more example in regards to this. And so this time, we have a water tank. And it's a spherical tank, a cone rather. Tank looks like this. The radius of which is 2, r equals 2, and that is 2 meters. The height of my tank is 4 meters. And it's being filled up with water. So we got water going into the tank. Right? So if the water is being pumped into the tank at a rate of 2 cubic meters per minute. Find the rate at which the water level is rising when the water is 3 meters deep. So we got our tank. So again, here's my middle here. So this would also be R for that level of water. And we want to find how fast the water is coming in. Right? So let's look in terms of our equations for this. So we got, in this case, so we got here V equals 1/3 pi r squared h. Right? We do know dV dt, because they gave us that. This was 2 cubic meters per minute. Right? We know the height of the tank, maximum height. We also know the radius at the very top of the tank. Right? So again, we want to take the derivative with respect to t. But as I fill up this tank, the r value is changing, the h value is changing. So I've got too many variables here going on. So I need to make it so I'm only going to have 2 unknowns, and I know one, so I can solve it. Right? So we got here that in terms of this triangle here is similar to this triangle. Right? And so we can make use of that to get rid of one of our variables here. Right? Right? And so we have r is to h as 2 is to 4. Right? And we're going to solve this, and we're going to solve it because we want to know in terms of the height. We're going to solve this for r. And the way you do this is you cross multiply and divide. And so R is going to equal 2h over 4. So R is going to equal h over 2. So now we're going to use this and plug that in there for my value. So we have V equals 1/3 pi R squared h. So V is going to equal 1/3 pi h over 2 squared times h. So let's do a little math on this first. So V is going to equal 1/3 pi. This will be h squared over 4 times h. And one last step in terms of simplifying. So this is going to give us 1/12 pi h cubed. So we have that. Now we're going to take the derivative with respect to t. So d dt. And so we get dv dt is equal to 1/12 pi 3h squared dh dt. So now we can take our numbers and we'll plug in. And so we got dv dt they gave us. So this is 2. 1/12 pi 3, the height is 3, so 3 squared dh dt. So this is going to be 2 equals 3 squared is 9, 9 times 3 is 27, so this is going to be 27/12 times pi dh dt. Solving for dh dt, we're going to divide. So divide this. Divide this. And we end up that dh dt is going to be 0.28 meters per minute. So we get the rate. So we have in terms of related rates. The next section deals with 2 other things. First off, being linear approximations. And so, for example, if I have a curve of some type, so let's draw in a curve, okay? And then at some point here, which will be A, and then this will be alpha A, as far as its coordinates. Okay. If I have the tangent line to this point, okay, and we have y equals L of x. Okay. Well, this tangent line gives me a pretty close approximation as to what's going on in that curve over a very small range of A. And so we have that y is going to equal f of A plus the derivative evaluated at A times x minus A. So let's get to how this works. So let's do an example here. So we want to find the linearization of f of x equals the square root of x plus 3 at a equals 1. Okay. And then use that approximation and use it to evaluate the square root of 3.98 and the square root of 4.05. Right? So let's go through and do this. So first off, I need to rewrite my equation. So we got f of x was equal to the square root of x plus 3. Well, then this becomes x plus 3 to the 1/2. Right? So rewrite. I want to take the derivative of that. So the derivative, f prime, is going to be 1/2 x plus 3 to the minus 1/2, and then the derivative of x plus 3 will just be 1. So it's right there. So if I rewrite this, this will be that my derivative is going to be 1 over 2 times the square root of x plus 3. Well, when a equals 1, we get that the f prime of 1 is going to be 1 over 2 times the square root of 1 plus 3. Well, 1 plus 3 is 4, square root of 4 is 2, 2 times 2 is 4, and we end up with 4. So now let's find our linear approximation. So L sub x is going to equal f of 1 plus the derivative, the value of 1 times x minus 1. So L sub x, well, the f of 1, if I take my original equation, which was here, and I plug in 1, 1 plus 3 is 4, and the square root of 4 is 2. So this will be 2. My derivative was 1/4. And then this will be x minus 1. So let's go through and do this and get our equation. So L sub x equals 2 plus 1/4 x minus 1/4. We have fractions, so we want to have a common denominator, which will be 4. So 2 is going to be the same thing as saying in over 4. And so L sub x is going to equal 7/4 plus x over 4. Okay. So now, for the square root of 3.98, we get that L sub x is going to equal 7/4 plus 0.98 over 4. And that'll give us a value of 1.995. And then if we do it for the other number, which was the 4.05, we get that L sub x is going to be 7/4 plus 1.05 over 4. And that'll give us a value of 2.0125. And you find out, if you just do on your calculator, square root of 3.98, square root of 4.05, you'll find that those two are pretty much right on the mark. Right? So you got in terms of linear approximations, again, back before you had the toy and you had to figure out these square roots, this was a way of getting a good value as to what they were. So the last thing for today then deals with what are called differentials. And so our derivative dy dx, which we said is f prime. So now what we have is one brand new step, and that is that dy is going to be f prime x times dx. So for example, if f of x is equal to x cubed plus x squared minus 2x plus 1. So we have that. Right? And I want to find dy. So first thing I'm going to do is find my derivative. Right? So we got the derivative dy dx is going to equal 3x squared plus 2x minus 2. We want to find dy, so the opposite of dividing is to multiply. So I multiply everything by dx. And we get that dy is going to equal 3x squared plus 2x minus 2 times x. So now let's say we actually want to find dy. So we want to find dy as x goes from 2 to 2.05. Right? So we have our equation here. So now what we got to do is just take our numbers we have and plug it in. So dy is going to equal 3 times 2 squared plus 2 times 2 minus 2. Right? And the change in x, when I go from 2 to 2.05, that change is 0.05. So we plug in the numbers, and we get a value of 0.7. So one more example of this, and that is, given the radius of a sphere, is 21 centimeters, with a possible error, with maximum possible error of 0.05 centimeters. What is the max error in value? What's the maximum error in the value of my sphere? So again, it's a sphere, so V equals 4/3 pi r cubed. We want to take the derivative with respect to r. So we get dv dr equals 4/3 pi 3r squared, which will become dv dr equals 4 pi r squared. So this 3 here cancels out that 3 there. Okay. And if I solve that for dv, so multiply everything by dr, and we get dv equals 4 pi r squared dr. Right? So we know, so now we can take our numbers. We got dv is going to equal 4 times pi times 21 squared times 0.05. And that'll come out to be 277 cubic centimeters. So we can talk about the error in our measurements. So we got relative error and absolute error. So relative error, first off, and we'll go in regards to the problem we were just doing, would be the change in volume over V, which of course would be dV over V. And so that would be our change in volume, which was 2.7. Okay. So we said our dV was 4 pi r squared dr. Right? We said this was 4/3 pi r cubed. Okay. And if I play with this and rearrange this a little bit, we end up that this comes out to be 3 dr over r. When I simplify that, and so this will be 3 times 0.05 over 21, and we get an error of 0.007 in the value, and that would be in terms of cubic centimeters. If I do this in regards to the radius, right? So the relative error in the radius would just be dr over r, which will be 0.05 over 21, which will be 0.0024. Okay. And then if I wanted to change those to percent error, for my volume, this would be 0.7%. And for the radius, this would be 0.24%. That's all I got to do is just move it over 2 places. Right? And so we have in terms of those. And with that, that will conclude this lesson.